In this video, I'm going to talk about energy stored in a coupled circuit. Coupled circuit is nothing but, you keep two inductors side by side and assume that there is a mutual inductance between these two. So our goal is finding total energy stored in each inductor as well as energy stored because of the mutual inductance. So if you look at energy stored in each inductor, energy stored in each inductor is nothing but half Li square joules. Now here two coils kept side by side, there is a mutual inductance M. Okay, now I connected an AC source to coil 1 L1. Current passing through this is I1 equal to I maximum sine omega t, and nothing is connected to coil 2. So what happens, because of the mutual inductance M, there is an induced EMF here. That value is L2 times, this value here is M times mutual inductance times di1 by dt. That's the voltage across this. But nothing is connected to coil 2, so there is no current passing through this. I2 equal to 0. Now we'll find what is the energy stored in each coil. So first P1, power consumed by the coil 1, P is nothing but V times I. So this is instantaneous value. So P1 of t, V1 times I1. Both of them are AC quantities. I1, V1, I can write it down as self-inductance, which is L times di1 by dt. So L1 times di1 by dt. That is the power consumed in coil 1. Here W is nothing but work done, which is energy. So work done equal to integral of P1 times dt. P1 is nothing but V1 times I1. So I1 is there and V1 is nothing but L1 times di by dt. Dt get cancelled. So L1 is constant. I pulled it out. So here this I1 times di, I1 is changing from 0 to maximum value. So it's a sinusoidal value. So it is changing from 0 to I. So 0 to I. So work done or energy stored in coil 1 is nothing but half L1 I1 square. That is energy stored in the coil 1. Now we'll find what is energy stored because of the mutual inductance and in coil 2. Now what I'm going to do here, to keep the energy stored in this coil constant, energy is stored in a coil because of the magnetic field, right? So to keep this constant, I'm assuming I1 is constant. Okay, so I1 is constant in this case. Now I'm connecting another source across coil 2. Now there is I2 current is passing through this. Now because I1 is constant, there is no induced voltage across coil 2 because of I1, because di1 by dt equal to 0. There is no current change. Now power consumed by coil 2 equal to V2 times I2. Okay, and at the same time, because of I2, current is flowing, current is changing at the same time. There is an induced EMF across this. That value is M times di2 by dt, which is nothing but V or induced EMF times I1. Now remember, this voltage produced by this coil 2 might aid to the already existing voltage or might be subtracting. That's all depending upon the Todd convention. Okay, at this point I'm not worrying about that. So total energy stored or produced by coil 2 or consumed by coil 2 equal to P2 times P2, which is V2I2 plus M times di2 by dt I1. Okay, I'm going to separate these two. So V2I2, V2 I can write down as L2 times di2 by dt plus M times di2 by dt times I1. Okay, so here dt get cancelled, same thing, dt get cancelled. So total energy stored in coil 2 equal to M times I1 I2 plus half L2 I square, I2 square. This is also I2. That's the total energy stored in coil 2 as well as total energy stored because of the mutual inductance. Where is that energy stored? That energy could be stored between those two coils. I mean, not physically between those two coils, but whatever the force existing between those two coils, that force, attractive force or repulsive force, it could be. So that force, we are saying that that's the energy keeping those two coils either attractive or repulsive. Now the total energy is W1 plus W2 half L1 I1 square plus half L2 I2 square plus M times I1 I2. So if it is attractive force, then we're going to take that as M I1 I2. If repulsive force, then minus M I1 I2. Now I want to find the upper limit of M. What is the upper limit for M? What is the mutual inductance value? So to keep it upper limit, I'm going to take the negative, half L1 I1 square plus half L2 I2 square minus M times I1 I2 must be greater than or equal to 0. Why didn't I choose plus? If I chose plus, when I take this to the other side, it will become minus M I1 I2 if I chose this as a positive. In reality, you don't have any negative M. That indicates that that is acting like a generator which produces energy. Inductor is a passive element, it cannot produce any energy. So that's the reason to find out the upper limit, I'm choosing this as a negative number. And I'm going to write this whole thing as a perfect square. Perfect square I1 square root of L1 minus I2 square root of L2 whole square. So this is the remaining constant. So to find out upper limit of M, I need to make this equal to or greater than, must be equal to or greater than 0. So M value must be less than or equal to square root of L1 and L2. That is the upper limit of M. Now if I take out that greater than or equal to, I will end up with a constant K. Okay, that constant K equal to M over square root of L1 and L2. K is nothing but coupling coefficient. There are no units for K, and K value is always between 0 and 1. That coupling coefficient K tells you what is the coupling coefficient or coupling factor between those two. So if its K value is 1, that indicates that these two coils are 100% magnetically coupled. So that means the coil 1 produces magnetic flux. If I connect it to the source, that magnetic field or magnetic flux is 100% connecting to the coil 2. That's when K equal to 1. K equal to 0, that indicates that those two coils, there is no magnetical connection. Okay, so here whatever magnetic field or magnetic flux produced by coil 1 is not connecting to the coil 2. Then the K value is 0. So K value is 1 is good, K value 0 is bad, there is no magnetical connection. Okay, so in this video we learned what is the total energy stored in a magnetically coupled circuit. I also introduced coupling coefficient K and the relation between coupling coefficient K and M value. I'll stop it here. Thank you.